We use the term small bodies in this course to describe anything smaller than a planet. This could include objects orbiting planets, like moons, and objects orbiting the Sun, like asteroids. Over the years, astronomers have developed two different ways of classifying small bodies in our solar system. The first of these is based on location. Depending on where something is, we give it a different name. So small bodies orbiting planets include moons and ring particles. Small bodies orbiting the Sun include asteroids, comets, and the trans-Neptunian objects in the Kuiper Belt and the Oort cloud. Historically, this approach came first. However, as we've begun to explore the solar system with spacecraft and more powerful telescopes, we've come to understand that the size and shape of a small body is also an important way of classifying it. Here, the fundamental dividing line is based on whether or not the body is large enough to be spherical. On the large side, we have the large and medium-sized moons and the dwarf planets. On the small side, we have the small moons, ring particles, and other very small bodies orbiting the Sun. This last term, very small bodies, is not a recognized term in the field. However, in this course, we'll use it to refer to anything orbiting the Sun that is too small to become spherical. This table summarizes all of the major classes of small bodies in our solar system. The areas left black are combinations not yet seen in our solar system, though they probably do exist. They just haven't been directly observed yet. So why do we make this connection between size and shape in small bodies? Of course, we sometimes make the same connection between size and shape in people. If you eat too much, you may become spherical, but that's not quite what's happening here. The shape of an object in space depends on the balance of two forces, gravity and the strength of the material the object is made of. Remember that every bit of matter has a gravitational pull. This means that every bit of matter in an asteroid, for example, is pulling on every other bit, trying to squeeze them all together into a spherical shape. On the other hand, the strength of the rocks, ice, etc. that the asteroid is made of are trying to resist the pull of gravity. If the material is stronger, the asteroid will keep whatever random shape it formed with. If gravity is stronger, the asteroid becomes round. However, making a body larger makes the gravity stronger without changing the strength of the materials it's made of. So no matter what an asteroid is made of, at some size, gravity takes over and makes it spherical. The boundary where this happens is typically around 400 to 450 kilometers diameter. The exact boundary depends on the details of the body's composition, temperature, etc. So it's a kind of gray area and will vary from object to object. For example, here are two moons that are nearly the same size. Mimas is the smaller one at 400 kilometers diameter. You can see that it's clearly spherical. On the other hand, Proteus is slightly larger at 450 kilometers diameter, and it looks almost cubical. These are both icy moons, and it may simply be that Proteus is colder, so the ice is a little more frozen. In other words, Proteus is the solar system's largest ice cube. The vast majority of small bodies orbiting the Sun and planets are much less than 400 kilometers across, putting them in the categories of very small bodies or small moons. Most of the things that these very small bodies and small moons have in common relate to the fact that they have very weak gravitational pulls due to their very small masses. The first property is the one we're using to define very small bodies, irregular shape. As we just saw, if gravity is weaker than the material, the body won't become spherical. Many, though not all of these bodies, are rubble piles. In other words, they aren't a single solid mass of ice or rock. Instead, they're made of many small pieces without much cohesion between them. This becomes more true as we move to smaller sizes. These objects may have originally formed as rubble piles, or they could have been broken up in collisions. Very small bodies and small moons often have heavily cratered surfaces. This reflects the fact that they are too small for volcanism or other processes that might erase the effects of impacts. The interiors of these bodies are often quite pristine. In other words, they haven't changed since they were formed, so they retain the individual grains of material that they formed out of. Here we're looking at an asteroid sample that came to Earth as a meteorite. On the very smallest objects, typically a kilometer or less in diameter, we see a phenomenon known as fluid dust. Here, the gravity is so weak that even the static charge on dust grains can compete with it. Electrically charged dust is able to behave like water, flowing across the surface and settling into low points in lakes of dust. We see that here on asteroid Itokawa. As we just saw, much of what makes very small bodies different is their weak gravity. A good way to quantify this is through the escape speed. Remember from the chapter on gravity that escape speed is the speed you have to travel to completely escape from a body and not fall back or go into orbit. In general, larger bodies have larger escape speeds, reflecting their stronger gravitational pull. Let's look at an example of calculating the escape speed. We'll consider the escape speed from comet Halley. Spacecraft have gotten close enough to Halley that we have direct measurements of its gravitational pull, so we know its mass as well as its average radius. As we saw earlier, the escape speed is given by the square root of 2 times the gravitational constant times the mass of the body you're escaping from and divided by the radius. Since the gravitational constant is in there, the mass has to be in kilograms and the radius has to be in meters. Since the radius is currently in kilometers, we'll have to convert it to meters. The conversion factor here is 1,000 meters divided by 1 kilometer equals 1. So multiplying that by 5.5 kilometers, we get 5,500 meters. As usual, we should do a sanity check here. Remember that there are 1,000 meters in each kilometer. So we should expect several thousand meters from over 5 kilometers, and that's what we're seeing here. We'll continue this example on the next slide. Now that we've got the units worked out, we can solve the problem. Start by writing down the equation. Then put in all of the values we know. Notice that all of the units are in there as well, including the units for the gravitational constant. Next, we multiply out everything on the top and combine all of the units. The meters on the bottom cancels out one of the meters in the gravitational constant. The kilograms from the mass cancels out the kilograms in the constant. Then we divide out the top from the bottom. Finally, we take the square root of the number and the units, leaving us with an escape speed of just over 2 meters per second. Notice that meters per second is a speed unit, distance over time. 2 meters per second is a typical jogging pace, so gravity must be very weak here. That makes sense for a body that's only about the size of a city. If you are standing on the surface of Halley's Comet, you could probably jump off of it. Now you should try doing one of these calculations. See if you can figure out the escape speed from Pluto. Before you do this, think about what you expect. Is Pluto bigger or smaller than Halley's Comet? That will tell you whether you're expecting a bigger or smaller number than what we saw in the example. Also, be careful of the units here. Remember that the gravitational constant forces you to use kilograms for mass and meters for radius. So you will need to do some conversions here. Finally, make sure you discuss how your answer compares to the escape speed from the Earth. Notice that this speed is in kilometers per second, not meters per second. So you'll need to do another conversion to make this comparison.
Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the escape speed section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit.
Now I'd like to run through the major groups of small bodies, starting with moons. A moon is a body orbiting a planet, asteroid, dwarf planet, etc. A sampling of the moons in our solar system is shown here. There are over 150 known moons in the solar system. Most of the ones we know about are orbiting the 4 biggest planets, although you see a few listed here that are orbiting dwarf planets like Pluto and Eris, and there's even one shown orbiting an asteroid. Here's a closer picture of that system, the asteroid Ida and its moon Dactyl. The number of known moons in the solar system keeps growing, and eventually we'll probably find that there are many more moons orbiting small bodies than there are orbiting planets. But we're only just starting to discover the moons of these smaller bodies. Not all of these moons are alike. Some are small chunks of ice and rock, barely held together by their gravity. Others are big enough that if they were orbiting the Sun, there's a good chance we'd consider them planets. As we study the planets, we'll also be considering their moons, especially these larger moons, since they provide more great examples of the processes that shape planets. The vast majority of the moons in the solar system are small, irregularly shaped objects that have more in common with asteroids and comets than with planets. Here are a few examples. Phobos is a moon of Mars and quite possibly a captured asteroid. Notice the impact crater that takes up most of one side of it. Prometheus is a tiny moon of Saturn. It's right at the edge of the rings, and you can see the effects of impacts from ring particles on its surface. Phoebe is one of several small moons that orbits its planet backwards. This is probably a sign that it was captured rather than forming around the planet. Finally, Saturn's Hyperion has a surface covered in odd-shaped craters, making it look like a sponge. In addition to moons, all 4 of the giant planets have systems of rings orbiting over their equators. Saturn's is the most famous set, and for good reason. It's much brighter and has much more mass than any other planet's ring systems. Planetary rings are made of huge numbers of small bodies orbiting the planet like a swarm of moons. The particles range in size from tiny grains of dust up to boulders or larger. Collisions keep the rings in a flat plane. Anything on a tilted orbit crashes into the ring plane repeatedly until it's back in line. In Saturn's rings, and in some of the other ring systems, most of the material is made of ice, though there is some rocky material and some organic carbon-rich material in several of the ring systems.